Welcome everyone. My name is Byuongho Jung, and I'm the one who will present the oil statistics overview in the morning session. So let me start. So I'm going to cover first the key oil trends, and then the key concepts of the oil statistics, and lastly, the key points for reporting oil data. First, key oil trends. So when it comes to the supply side, the world's largest source of primary energy in 2018 is found to be the oil, accounting for around 32%, and followed by the coal, 27%, and natural gas, 23%. And there is a changing of production landscape in 2016. Saudi Arabia, and followed by Russian Federation, is one of the toppest oil producer in the world. On the other hand, since 2017, United States surpassed the other two countries like Russian Federation and Saudi Arabia, and they are becoming the #1 oil producers in the world since 2016, and that is consistently true even in 2019. When it comes to the refining and demand side, most of the growth in refining has taken place in the Middle East and Asia, Oceania. And the China solely is showing like 6% of increase in 2018 compared to 2017. And growth in oil demand is also driven mostly by non-OECD countries, including China, and non-OECD Asia and non-OECD Europe. And on the other hand, the demand by OECD side has been decreasing, as you can see on the right-hand side graph. And obviously, like last year, there was an impact of COVID-19 on oil demand. As you can see in these both graphs, you're looking at the road transport activity on the left side and the number of flights on the right-hand side. And around February, like already China took the measure of the lockdown in earlier, so which led to the decrease of the road transport and number of flights activity, and around like 50% of decrease, year-on-year decrease around the world, starting from March. And as you can see here, it is really important to track the oil data in a timely manner to identify what caused this deep drop of the oil demand. So it is very important to understand the general understanding of the oil statistics. And that brings me to the next slide, which is the key concepts of oil statistics. Let's first take a look at the oil classification. First, we're looking at the primary side of oil products, and there is a secondary side of oil products. And the link between these two, we can say that is due to the refineries. So first, like primary oil products, we define that the oil products that is not processed by the refinery plants, that are composed of crude oil, condensates, natural gas liquids, in short NGL, and synthetic crude oil and shale oil. And then on the finished secondary oil products, there are a various number of oil products, as you can see here, and all the detailed description and definition of each oil product can be found in the IRS guideline and also in our joint oil annual questionnaire instruction documentation. And lastly, like there is also secondary products that are input to the refinery, which are additive, and also the refinery feedstocks. Let me give a more detailed information in the later slides. Before I go further, there's one thing that I'd like to highlight further here, which is the condensates. This is the very light and versatile hydrocarbon. And there are two types of condensates that we are collecting the data, and those two are reported in a separate manner. So the one type of condensate, we call that as a field condensate. So it is recovered from associated and non-associated gas fields. and is normally intermixed with the crude oil stream. What is the associated and non-associated gas fields? If it is related to the oil, we call that as associated gas fields. If not, we call that non-associated gas fields. But we have another special lecture for natural gas just after me, so you will hear more about this special distinction between these two gas fields. And there is another type of condensate here, which is the plant condensate. So these are the one recovered in natural gas processing plants or separation facilities. So depending on where it occurs, where it originated, we distinguish these two condensates. Okay, so let's take a look at this time the classification, the criteria as to how we can classify each type of oil products. So we have first density, sulfur content, and energy content here. So first density. As you all know, like this is the specific gravity or density, like when we use to convert from the mass unit to the volume unit, or vice versa. So most of the oil is lighter than water, but there is still like extra heavy oils, which has a higher density than normal water. On your right hand side, we're watching the one small graphic here. There is oil sands which is heavier than the water. The unit used here is the API, the American Petroleum Institute. That's what it means, and it's the kind of like calibration to indicate how much heavy or light the oil is. There is another classification here, which is sulfur content. So if there is a high sulfur, we can say that the oil is sour. And if it is less sulfur, we can say the sweet one. And the more sour the oil is, then the price is more expensive. And finally, these are the concepts that are already covered in the previous presentations, which are like energy content or net calorific values or gross calorific values. Here, it is very important once again to collect all this information by flows because the characteristics of this NCV really depends on if it is at the production stage or import or export stage. So I want to highlight that it is very important to separately to collect the data for each flow. And obviously this is very essential when we convert from the commodity balance to the energy balance and eventually to derive the CO2 emissions calculation. So crude oils have a wide range of physical and chemical properties. As you can see here, we normally say that the OPEC oil has a characteristics of heavy and sour oil, and non-OPEC has the light and sweet oil. And depending on these characteristics, the yield from this crude oil, the refinery yield, really vary depending on what's the input to the refinery plants. And there is one point that we normally use when we validate the data. It is already mentioned by our colleague Julia in the first day about how to validate our energy data. This is to see the refinery specification, because normally the configuration of the refinery plant is always like stable. It is really expensive to change that configuration. So when we look at the graphs here from 2001 to 2015, we see that most of the years have the similar share of the refinery products. But there is one anomaly found here in 2011, which shows that there is a less residual fuel oil production. On the other hand, like gas diesel production is increased substantially. So from this, we can raise this issue to the contact if the reported data is correct or not. So this is very great tool to validate our data quality. So by far, what we learn is the oil products. Which kind of oil products we have? from now on, I'm going to cover like the flow, the journey of our oil products from production to the end users. So first, let's take a look at the supply side of the primary oil products. The journey begins with this indigenous production. So indigenous production is composed of this process. First, the wellhead production. So at the well, the extraction of the crude oil and also the associated gas is performed at the onshore and the offshore wells. And there is a processing needed to purify and also to remove the other unwanted materials. And then after this, it becomes the marketable production. I mentioned in my first presentation, which is fundamentals of energy statistics. When it comes to the indigenous production, we're always dealing with the production data that is in the marketable status. So for crude oil and field condensate, plus the natural gas liquids and plant condensates feed into our oil balance. For the associated gases that are also produced from this well will feed into our natural gas balance. And there is also the one flow called from other sources, which includes, for example, if there is a biofuels for blending with gasoline or diesel, and these feed into this flow. And we have a trade for exports and imports. And there's obviously a stock build and draw. So we represent it as a stock changes in our balance table. And there's very interesting flow here, which is the petrochemical industry. As petrochemical industry is more and more evolving, it also produces some oil products that goes back to the previous stage of refinery process. We call it as a backflows. So these also feed into our supply of primary oil products stage. And some of the primary oil products can be directly used without going through the refinery process. And we report that amount under this direct use flow. And here's one flow again, which is products transferred. This refers to the amounts of oil products, secondary oil products that needs further processing. So it appears here at this supply of primary oil product stage because that will go into again to the refinery plants. And then we get to the refinery processing plants. And then next stage is to see the supply of secondary oil products. So even after this refining process, there's also a bunch of journeys waiting for us here. So first, after the processing, we've got finally the refinery gross output. We can have LPG or naphtha, gasoline, or a fuel oil. And then some part of those fuels can be used in support of the operation of the refinery plants. We call that as a refinery fuel. And then in between these products, it can be transferred to the another product. For example, to when the characteristics of certain oil products is changed, then we use this flow in interproduct transfers to represent that process in our energy balance. So these are the general rule of thumb, to validate if that reported interproduct transfers data are proper or correct or not. So there are some possible cases and possible but not very likely and not likely cases. So more generally, heavy to light products is not likely happening. So these are the basic rule we can apply when we validate and verify our data collection. And of course, some part of it goes to the products transferred. For example, if naphtha is imported in one country but they think that it needs more processing, then we report this number under this products transfer flow, and it goes back to the primary of supply of primary oil products, the slide we just saw before, and then it goes back to the refinery processing for the further processing. And there is a primary product receipts. This refers to the amount of primary oil that is used directly. And finally, some of the products that are delivered to the consumer needs to be recycled. Then this is also taken into account at this stage. And international marine bunkers, these are one of the key flows that consumes a lot of amount of oil products. So this is represented here. And we also have a trade for secondary oil products. And also stock change is applied here for our secondary oil products. And finally, going through these all stages, our secondary oil products will be delivered to our end users, including industry and also our residential and commercial sectors. And here's one thing I want to mention here, which is the transformation efficiency. Like when we want to transfer from one type of fuel to the another, there is always like losses occurring. So this is to highlight that point. This is also mentioned in our Julia's and Louis presentation on first day about how to validate our data. So refinery yield is calculated by using the refinery intake and also the output. So depending on the results, we can conclude that there is a refinery gains if refinery gross output is bigger than refinery intake. And we can say there is a refinery losses if refinery intake is bigger than refinery gross output. But here, one thing very important here is that the unit really matters. So when we talk about the mass and energy units, we don't physically and practically expect to see the refinery gains. On the other hand, like when we talk about data in volume units, the refinery gains are still plausible and need to be validated by using the calorific values. And when we convert from the volume to energy or mass, then we can validate that the reported data is correct or not. And I mentioned earlier that international marine bunkers are really like the source of of our consumption of oil products. So this flow covers the delivery of oil to ships of all flags undertaking an international voyage. So there is a separate flows for domestic navigation and also for fishing. So this is only to take into account the oil consumption that is fueled into the international voyage ships. So it is purely dependent on the port of departure and port of arrival, irrespective of the ownership of or national flags of the ship. Why it matters? Because this is important outlet for the refinery industry, and the demand is always like it's going to be very substantial. And here, 80% of global trade in physical goods is done by sea. And finally, it is very important to collect this data separately, because when it comes to the national inventories for CO2 calculation and also greenhouse gas calculation, this amount of oil for international navigation is deducted from that calculation. So it also applies to the international aviation bunkers. And due to their specific properties, a lot of oil products has their own uses. So here we are looking at some examples here. Jet kerosene is mostly used by aviation. Bitumen, for example, is mostly used to pave the road or for the roofing material. So it is reported under non-energy uses. And crude oil sometimes is used as the electricity plants to generate electricity, which is the case for Japan. And so there is an expected consumption and usage of oil products. So this is also a very good tool to validate our data. So this brings me to the final section here. I'm going to cover specifically how our joint oil annual questionnaire is structured and how do we report using that annual questionnaires. So these are the types of fuels we just dealt with, and there are like around 6 in the aggregate level, like 6 tables is comprising our oil annual questionnaires. And these tables, I think it is already covered in the other fields as well. They are interconnected. So it's like a live creature. So we need to really think about how the reporting data in one table impact to the another table. And our joint annual questionnaire has the function to validate these things automatically. So this is something that we want to encourage the other people also to use and to have a look how it is designed to identify what's missing in reporting, and also to make sure that we don't double count any amount of oil. So there is one specific very difficulties that I have been asked from our users when it comes to data reporting. One of that is the natural gas liquids. So NGL, this is the liquid or liquefied hydrocarbons recovered from natural gas in separation facilities or gas processing plants. So they are composed of ethane, propane, butane, and pentane, etc. And the thing is that the heavier fraction are usually processed in the refinery plants. On the other hand, the lighter fractions are generally used directly. So there are a couple of cases. First, when it's processed in a refinery because it's heavier, in the table 1, we report the amount of indigenous production here, and then in another table, we report that as because it goes through the refinery processing. So in this case, the motor gasoline is produced. So 100 kilotons of NGL is transformed to this motor gasoline, and this appears in table 2A in our joint oil annual questionnaire. Another case, what if the natural gas liquids is used directly? So as I said earlier, lighter fraction of NGL can be used directly, and in table 1 there is a specific flow as a direct use. So if 50 kiloton is produced, and if it is used directly, then we report under the direct use flow. And if it is used as a NGL, then it might be the case where it goes to the transfer. So for example, if it is used as NGL, then on your right-hand side, you see that the 50 kiloton of NGL is, maybe it's better to use the highlighter here, laser points. Then 50 kiloton of NGL is once again reported under interproduct transfers with the negative sign because it is removed from this balance. And there is another point here when it comes to data reporting, which is also very one of the very difficult reporting, which is the biofuel. I believe yesterday in the renewable sections presentations, this was covered, how to report biofuels in renewable and oil annual questionnaires. In oil annual questionnaires, it is the blended amount of biofuels is only concerned here. On the other hand, renewable questionnaire is only dealing with the pure one. So let me give you a little simple example here. First, there is a primary oil products, so which is table 1. So if there is a risk from other sources flow, report 100 kiloton. So let's say this is a biofuel, and then we know that it is biofuel. And first we report here because we know that, and then it is considered as additive and oxygenates column. And then if it is blended for the gasoline or diesel, then we report under direct use. And as you can see on the right-hand side, on the another table, we report first as a 100 kiloton under primary product receipts, because this is the primary product that are received from the renewable questionnaire side. And then obviously there should be some amount of gasoline that are produced through the refinery processing. So combining these together, the total 1,300 kiloton of motor gasoline blended with biofuels are reported here. So to be consistent with the renewable questionnaires, what should be reported in the renewable questionnaires? The only 100 kiloton that are destined for blending should be reported. So this kind of stuff are very maybe confusing, but when you use our joint annual questionnaires, then there is a specific tool that helps you to verify if the data is correctly reported. And then there is also very difficult flows as well, like very dynamic word in oil industry, which is petrochemical flows. So in the oil questionnaire, there is a specific table for the data reporting for petrochemical sectors. We deal with this separately because it is evolving in a more complete way. So we now have a refinery, and also there is a refinery output. And some part of it is delivered to the petrochemical industry. And here we have two cases. One is the oil products that are delivered to the petrochemical industry is used for energy uses or non-energy uses. And then out of it, like some part of it is there is an output from energy output, and there is non-energy output. For example, if we use the naphtha that are going through this petrochemical industry to produce the plastic, for example, the output, we call that as a non-energy output. And if it is, if the produced products will be used for energy purposes, we call that as energy output. Then where does it go? We call that as a backflows because it goes back to the refinery processing plants for further processing. So that's why we have a separate flows, backflows to refineries, and we report this amount of fuel into here. And then some part of it doesn't go to the refinery processing can be directly exported or sold to the consumers. So in our oil balance, what we include all oil inputs. And when it comes to output, only the output that are supposed to be used for energy purposes. What we shouldn't include? We shouldn't include the output that are used for non-energy purposes, like a plastic or fertilizers, etc. When we want to calculate the net deliveries to the petrochemical industry, then this is defined as the gross deliveries minus the backflows to the refineries. Otherwise, we might encounter the double counting issue. So this is the end of my presentation.
So thank you, everyone. I'm with Matthew today to talk about natural gas. So similar to the presentation you just had with Byuongho. We'll take you through a couple of trends and then specific gas concepts, and finally we'll try to to give you an understanding of how we collect gas information in the IEA's framework. So starting with the trends, when you look at the past 40 years in natural gas in terms of production, natural gas production has almost tripled. And now gas stands as the second largest growth contributor to global energy growth, right behind coal. And when you look at the biggest producing countries, you have the USA that are the biggest producers, followed by Russia. And when taking the two of them together, they now contribute more than 40% of global natural gas production. So basically, production of natural gas really expanded earliest and most quickly in those two regions following the Second World War. And there was a kind of relationship between the availability of natural gas supply and the rapid industrial expansion that they experienced. So profitable production of natural gas also relies on accessible demand markets for it. So natural gas has technical characteristics that make it very useful and flexible as a fuel in case that you have the necessary infrastructure to deliver it. And it can find several uses in different sectors, such as power generation, industrial sector, residential and commercial. So traditionally, the breakdown between those different sectors was evenly split, but very recently, the macroeconomic shifts and the supply competitive dynamics between fuels have caused the proportions to be much more in favor of power generation. So another important driver of natural gas use is to know precisely when it's going to be demanded. Natural gas demand experiences varying degrees of seasonality, and depending on the sector that you're looking at, it might peak at different moments throughout the year. So if you take the example of the United States, during winter time, you will have more demand for uses to heat up space, for instance, while during summer, you might be consuming more in the power sector to turn on the air conditioning. So in 2018, you have 40% of global natural gas that was used to produce electricity and heat. But now, also given the changing regional supply and demand dynamics, there is an increasing focus that's being put in moving natural gas internationally so that to match excess supply with places where there is demand. But moving natural gas is something that's very capital intensive in terms of infrastructure. You need pipelines to move gas across land. You need LNG infrastructure to move it across water. So last year we had about 30% of the natural gas produced in the world that was subsequently traded. And if you look at the biggest market players, you have Japan and Germany that are the biggest importers, respectively in LNG and in pipeline gas, with about 100 BCM each. A quick note on LNG and natural gas by pipeline. Those two things are exactly the same commodity, energy commodity. It's not two different products. As you have seen in oil, you might find different oil products. In this specific case, it's the same thing, okay? We don't make any distinction. The reason why we make a distinction in the way we collect the information is really because of the specificity of LNG and the infrastructure required to process it. Another natural gas benefit is that it has the lowest emissions per energy units burned when compared to coal and oil. So it's basically the cleanest fossil fuel. And that's the reason why many people believe it's going to be a bridging fuel in the transition to cleaner energy systems. So now, even though in terms of natural gas demand, this level was multiplied times 3 since 1973, natural gas is still the third source only after coal and oil in 2018 with a share of 23%. And if you look at electricity generation, its share is also 23%. At the country level, the relevance of natural gas in the mix depends on many different reasons. if you think from an industry perspective, there have been demographic shifts, also environmental policies on industrial emissions, different labor rates and things like this that have driven heavy industrial and energy intensive manufacturing activities to change location from OECD countries to developing countries. You can think of China, for instance. But more recently, there have been changes in the availability and the cost of natural gas in the United States from fracking technology, and that has the potential to reverse this kind of trend. So we'll see what happens in the coming future. And if you look at things from a power generation perspective, where natural gas is only the second to coal in terms of the share of energy supply in the global electricity generation, this share is expected to grow over the next few decades as a response to both economic and also environmental limits of coal generation, at least in cases where natural gas is a viable alternative. So this fuel switching may increase or may decrease the proportion of gas supply, the proportion of energy supply that's met by natural gas. And on the diagram on the left, you can see that while the share of natural gas in total energy supply for India and for China is still very small if you compare it to the world average, it's below 10%. In other places like in Japan, that basically imports almost all the natural gas that it consumes, the share is much higher, around 20%. And if you look at the biggest producing countries as well, like the US and Russia, they have much higher shares in natural gas, around 30% and 50% respectively. So I'll be moving to the key concepts now. When you think of natural gas, to some extent, it's very similar to oil because it has the same organic source material and it has comparable geological conditions in the way it's being formed. The main difference are the pressure and the temperature ranges at which it's being formed. So this actually leads to a more complete conversion of the organic matter into lighter hydrocarbons. And basically the lightest is methane. So that's why we usually define natural gas as being a combustible mixture of hydrocarbon gases that contain a very high concentration of methane. So most of the time, more than 90%. As you saw for oil just before, unlike what you saw with oil just before, natural gas doesn't have different products. It is a single product, and even though it can have different calorific values that range from 73 to 42 megajoules per cubic meter, it is a single product. And finally, because most of the time we will be measuring volumes of natural gas, we need to define the pressure and the temperature at which the measure is being done. So in the case of the IEA, we use the standard conditions, and this corresponds to temperature of 15 Celsius degrees and 1 atmosphere of pressure. Moving to the overview of the gas balance. So I think you're getting pretty familiar with this structure. On the top part, you have supply, and below you get demand. And those two information are coming from different sources. And theoretically, we should have a perfect match between the two, but it's never the case. And it shows in what we call the statistical difference. And that's a figure where we put a lot of effort because we want to keep it as low as possible. But having, as it was explained in the previous days, having a statistical difference of 0 is not necessarily a good thing. Now I'll be focusing on production. So production, natural gas obviously can be found in gas fields, but also in other fields such as oil and coal mines. And after the extraction, you obtain a first form of gas, the raw gas, that comes directly out of the well and still includes a number of hydrocarbons and other contaminants along with methane. And all those contaminants you want to get rid of through a series of chemical and thermal processes to make the quality of natural gas suitable for the distribution networks, for the pipelines. And so that's why you resort to flaring or venting when natural gas cannot be processed or transported to a gas treatment plant. And in some specific cases, you can have also a reinjection of this natural gas to enhance the production of the fuel. But at this step, the concentration of methane as a raw gas is not very high. And after it's extracted and transported and processed, you can have a concentration that moves from around 70% to sometimes up to 99% of methane. So this is a process that is a bit less complex than the one you find in oil refineries. And basically what's happening is that you make the separation of methane from other hydrocarbons. So you remove all the natural gas liquids, you remove crude oil, and you remove all the impurities like condensates, water, and carbon dioxide and sulfur. So those gases that are actually very rich in liquids, we call them wet gas, and they have a high concentration of NGL. And as a result, they are relatively high in energy content per volume. But after the purification process is done, the resulting gas is called the dry marketed production gas. And this is the definition that we use at the IEA when we talk about production. Additionally, we also have a classification for production flows. So we have associated gas in the case that it comes from a well where you also had oil. And in the case that it was only gas present in the formation, it's called non-associated gas. And in the case that it comes from coal mines, it's called colliery gas. A quick comment on associated and non-associated gas. So usually those we refer to as conventional gas, but you can also find gas in other types of formation that contain natural gas, like coal seams or shale rock and so on. And those sources are unconventional gas. And they usually require different technologies or different extraction methods to be accessed. So you can think of tight gas, shale gas, and so on. Now I'll be moving to the supply chain and the commodity flow of gas. So in terms of data collection and methodology at the IEA, we really try to cover all of the stages going through the supply chain. So we start from production of natural gas. So as we just saw, natural gas can be produced in the usual underground deposits, but also can come from other sources that are then blended into the grid. So we'll be considering those different sources, and then we will collect also information about the infrastructure. So the infrastructure that connects this production to the consumers, which corresponds to all the transmission and distribution systems, and also all the facilities to store gas under its gaseous form or LNG. And finally, natural gas is being consumed in different sectors. So those sectors, I think you also are getting very familiar with, transport, residential, commercial, and so on. And another very important aspect of this picture is the trade flows, because obviously you can also import and export gas through pipeline or under LNG form. And next step is trying to present the interactions with those arrows between the flows and the infrastructure. So at first we have all the natural gas that's being produced or blended in the mix, or even imported by pipeline. That's then going to be mixed into the transmission pipeline system. And in the case you import LNG, you have first to regasify it before you can mix it to the transmission system. And at this step, as you can see, it is possible to have power plants that are big enough so that they are directly connected to LNG regasification terminals to consume natural gas. But otherwise, you move from the transmission system to the distribution system. And after entering this infrastructure, gas is being slowly depressurized, and then it's going diverted to all the different gas customers that you see in green on the graph. Pipeline exports usually leave transmission system directly, while the LNG export, they come from the LNG liquefaction terminals. And finally, to balance this entire picture, you also need interactions between LNG and gaseous gas storage facilities. Okay, so now we're going to see a couple of those elements individually. So I'm moving to trade here, pipeline and LNG. So at the left, you have a pipeline trade, just for the anecdote and for the information. So the very first pipeline appeared in China, way before Christ actually, and it was made of bamboo. So obviously today we no longer have bamboo pipelines, but there's still a very cost-effective way to transport gas across land, and sometimes also underwater when it's small distances and it's shallow distances. And we find many interstate and local pipelines that exist to move gas over short distances. And when you think of major pipelines that cross international borders, they tend to be much more larger in terms of infrastructure, but also much less common. And most of the pipelines that actually move gas internationally are devoted to bringing natural gas from the producing countries nearby, like Russia, as you can see on the map, into the European transportation and distribution grid. So that's mostly because Europe basically only produces half of the gas that it consumes, so it really needs to import all the rest. And yeah, you find other types of pipelines in the world that are not shown on this map. While pipelines are still useful to transport gas over land, when it comes to moving volumes of gas across water, it creates a much more difficult and well, both technically and economically challenging situation, because the energy per volume is getting too low. So that's why you end up with situations where you have stranded gas in some places that cannot reach the market, and on the opposite, some places that cannot access the gas sources. So the alternative to that is to cool down natural gas and bring it to a temperature where it can become liquid. So this temperature is minus 162 Celsius degrees. And this is how you obtain LNG. So that's why that's exactly the same product as gaseous gas. It's just a different physical state. And this LNG is going to increase the amount of natural gas energy that you can store in a given volume by about 600 times. So that's very significant. And resultantly, it can be more cost effectively transported in special ships over much longer distances. But this entire process is very capital intensive and requires several components. So first you need a liquefaction plant. So obviously to liquefy your gaseous gas into LNG. You also need specific ships, specialized ships that safely transport gas to destination. And they're so specific that basically once they have delivered the LNG, they cannot transport anything else. So economically speaking, they are really, really difficult to make commercially viable. And finally, you need a regasification terminal to turn back LNG into its gaseous state. So in terms of trends, due to the different capital requirement in each of those components, you usually find many more regasification terminals than liquefaction terminals on the market. So in 2019, the globalization of LNG continued, and you still find only 25 countries with the liquefaction capacity against 42 countries with the regasification capacity. And last year, around 62% of global trade was made through pipeline still. So even though you have countries like the USA and Australia that are increasingly increasing their LNG exports capacity, you still have the main pipeline flows, such that the imports in Europe, trade in North America, and so on, that represent the biggest chunk of natural gas trade. Moving to stocks here. So natural gas is also a source of potential energy, and then it can be stored and used in different time and different place from which it's being obtained. And the direct benefit, obviously, is this association of the production and the consumption of this energy, provided that you have the storage mechanisms. So in the specific case of natural gas, it's often used to shift a level of production that's constant, so that to match seasonal fluctuations, as you can see on the two graphs here. So The thing with natural gas is that it faces unique challenges that you do not have in other fuels, such as coal and oil. Coal can be easily piled and stored, and petroleum products can easily be, poured into tanks. But in the case of natural gas, you really need to completely contain it to avoid escape. And you also have sometimes to compress it to allow reasonable amounts of energy to be stored in a given amount of space. So those characteristics increase the amount of physical, financial, also capital requirements when it comes to storing gas. In terms of storing solutions, you'll find mostly underground options, such as depleted reservoirs that are the most economical solution so far. So overall, stocks are going to provide this flexibility, this seasonal flexibility, and there is a combination of price signals and market regulation that will determine the operation of gas storage. So basically, during summer month, you'll have lower demand, so you will be building stocks, and during winter, you will be delivering to the market those stocks. Moving to demand. So finally here, we're looking at the classification of the different sectors. I'm sure you recognize most of them, from transformation, energy sector to total final consumption. So here, I'll be focusing on 3 of them that might be a bit less intuitive to understand. The first one of them is transformation sector. So basically here, we're trying to collect all the volumes of gas that are being transformed into a different energy form. So if you think of electricity, for instance, and in the energy sector right below, we're trying to collect the volumes of gas that are being used in the production of the energy. So when you're running oil and gas production activities, or when you're running a refinery, you will collect the volumes of gas that are being burned, but not transformed into another energy form. And finally, in the case of non-energy use, here we want to see all the volumes of gas that are not used for its energy content, but that are used as a feedstock to create raw materials, hydrocarbon based. So a very good example are plastics in this case. Finally, for this section, here is a slide that shows examples of transformations in natural gas. So on the left, you always start from the natural gas, and at the top right, at the end right, you'll find the different other energy forms that you can turn natural gas into. So from electricity to oil products, going through all the coal byproducts. So now I'll leave the floor to my colleague Matthew, who is going to take you through the collection of those gas data. Share my screen though.
So hi everybody, can everyone see my screen?
Not yet. I think I'm still stuck there. Sorry. Okay, should be good now. Yep,
I think that's good. Thank you, Louis. So yeah, once again, thank you, Louis, and hello everybody. My name is Matthew, and I'm just going to be going over the collection framework that we have here at the IEA. This is where we collect data on the full value chain of natural gas, as Louis very kindly summarized. In the slides that follow, you may see some similarities with some of the fuels we've already seen, but I think it's very important just to clarify some of the unique points which relate to natural gas reporting. So, for natural gas, our annual questionnaire collects data within 6 major categories with a number of sub-related tables. I'll go through these very quickly now, but we'll cover each in more detail soon. So the first table collects information about the supply of natural gas. This is the production, the total exports, imports, stock changes, as well as it includes an aggregated value for consumption. The next tables relate to consumption flows. So the first collects data on the transformation sector, the energy sector's own use, and also distribution losses, while table 2B pertains to final consumption in end-use sectors. Tables 3 and 4 then capture the natural gas trade flows of a country. So this is both for pipeline flows and liquefied natural gas flows. And then finally, tables 5 and 6 collect data on the natural gas infrastructure of the country. So this is storage capacities, liquefied natural gas facilities, and information around connectivity to gas networks, so whether they've got pipeline connections and so forth. So within these tables of the gas questionnaire, we do have some interrelations to one another, as shown in this slide. Even though there are separate flows, there is a need for consistency between certain values and aggregates, which we internally use to validate the data and check it. So for example, the level of consumption reported in table 1 should match the total consumption calculated in table 2. And similarly, the total import and export values reported in table 1 should match the sums of imports and exports in tables 3 and 4. There is also a need for consistency between related questionnaires, I think as Byuongho mentioned in his presentation. So for natural gas, for example, the input to electricity and heat production should match with the electricity and heat questionnaire reporting. And the receipts from other sources should also match their corresponding questionnaires as shown in the slide. So now moving on to the questionnaire itself. So this is an example of table 1, which relates to the supply of natural gas. I should highlight that we ask for 3 different values for each flow. So we ask for volume in million cubic meters. We ask for terajoule values, as well as average and net gross, average gross and average net calorific values as well. These calorific values are particularly important as we'll use them we'll use them along with data from other tables to do some calculations, which I'll explain soon. So on this table, there are a few nuances I'd like to go over. So when filling the table in, we only ever want to count the dry marketable production of gases. So this is once it's been cleaned of any impurities. We also don't count any gases vented, flared, lost, or re-injected within indigenous production. For trade, there are 2 points to note. So firstly, we only ever want to count gas when it crosses the physical boundary of the reporting country in the reporting year. And secondly, we don't want to account any transit or re-exports within these numbers. So when looking at STOG reporting, we only ever ask for the recoverable gases. So we don't count any cushion gases, which is the gas that maintains pressures in storage reservoirs. So we don't count those figures within our reporting. So the next table, which relates to consumption, in this we only collect data in terajoules. And we, again, like I mentioned, we use the gross calorific values that were reported in table 1 to convert to volumes. So this is why it's very important to make sure these gross calorific values are correct. The table itself is split into 3. So the first records the transformation sector, so when gas is transformed into electricity or heat. The second looks at consumption by the energy sector itself, so the gas consumed to support production or transformation activities. And the third figure records losses due to transportation or distribution. So table 2b, which is similar, this is where we ask for data on final consumption within sectors such as transport, industry, and other sectors. We distinguish between the energy and non-energy use within these sectors. So this is when gas is used as a fuel compared to when it is used as a raw material. So for example, to produce hydrogen is a common example. And again, in this table, we only ask for terajoule values, and we do the conversion to million cubic meters separately using the gross calorific values reported in table 1. So I'd now like to take a moment to go over some of the one of the technical aspects of reporting, which relates to the transformation sector. So there are, as I think has been covered before, there are 3 types of technologies or plants. These are electrical plants, heat plants, combined heat and power plants. But within this, there are 2 types of producers. The first are enterprises whose sole or main purpose is to produce and sell electricity or heat. These are classified as main activity producers. The second are entities that produce and consume electricity or heat with the aim of carrying out another primary other activity. And these are classified as auto producers. They may then sell on any excess heat or electricity that they produce, either back to the grid or to other organizations. So the important thing to note when filling in tables 2A and 2B is that for auto producers, as the table shows, that all electricity production should be reported in table 2A, while for heat in table 2A, we only ever want to count the gas used to produce the heat that is then sold onwards by the auto producer. So we don't want to record the gas used for producing heat that is then consumed by the enterprise itself. This should be reported in table 2b. So moving on, so tables 3 and 4 look at trade, and they're fairly straightforward. We collect data for this in both volume, million cubic meters, and terajoules. The data is asked for as both a total and as a liquefied natural gas value. So to clarify, columns A and C should include the liquefied natural gas values reported in columns B and D, along with any gaseous gas traded. The export version of this, table 4, is identical, except it asks for the country of destination rather than the country of origin. So before I finish, there are a few limitations specific to gas reporting that I'd like to quickly go over. Firstly, unlike some other fuels, such as coal, we do treat gas as a single product in a single questionnaire. We know there are often gases with both high and low calorific values used in different gas systems within a country, but instead we do ask for countries to report the average calorific value for their gases. And as I explained, making sure these average calorific values are accurate and correct is very important, as we do use them to do conversions. The second comment I have is related to trade. So with the liberalization of the market and the development of new technologies and innovations, there are now increasing amounts of trade, as Louis mentioned. And in particular, we do see more transit trade. But while this can be difficult to remove and account for from reporting, it is very important to us, and it helps us to create accurate and insightful data. The final problem we do sometimes encounter is around the measuring of gas volumes. So we at the IEA, I think, as Louis did mention, we use the standard conditions for measuring our volumes. So this is 15 degrees Celsius and under 1 atmosphere of pressure. But sometimes we do find data reported to us under different conditions, which just requires us to make some conversions to make sure it's comparable with other countries and within our databases.
So welcome everyone to this session on energy balances. I'm very happy to be here today to present this session to you with my colleague Nicola. And as you have seen over the past few days, you have been looking at the different fuels separately, but you can really improve your understanding of those statistics if you can put it in an energy balance. Before I start with the presentation, I will just emphasize that if you have any questions, at the end of this presentation, there will be a question and answer session. But if you have a pressing question that you want to raise with us because it's not allowing you to fully understand the presentation, then do not hesitate to drop it in the chat box or raise your hand, and we'll interrupt the presentation to answer you. So this presentation, it will be divided into 5 parts. First, we will see what is an energy balance, how it differs from the commodity balances that you have been looking at, and also how the IEA energy balance is constructed. Then we will study why is it so important to calculate an energy balance and the advantages you can derive from it. Third, we will see the methodology behind the energy balances, the definitions that we use, etc. After this, I will pass over to my colleague Nicola, who will present to you how the IEA energy balance looks like, and also the different uses that you can derive from it, such as the calculation of CO2 estimates or indicators. Before we start with the technical part of the presentation, I would like to do a warm-up question to better understand the audience. So we will use the menti.com and to answer this question. So I would like you to answer the following question. Is your country producing a national energy balance? You have three choices, yes, no, or are you currently developing it? So please go to menti.com and use the code 63, 46, 58, and 85. I give you a few seconds to answer this. We know that many countries already produce energy balances. At the IEA, we collect information on many countries, but some of you may be currently developing it or have not yet started doing it. For the moment, no one is answering. Does the code work?
Yes, the code is working, Zakia.
Okay. Because
let me just do a quick check. Could you please, in your reaction, all of you who are at the meeting, click on the yes button. Okay, I see some people are mentioning in the chat that they are answering and they have submitted the answer. So maybe you need to refresh.
Yeah. Oh, okay. So we see that 21 people have answered yes, which is great. And what I was thinking of, so most countries, most of you here already have energy balances in your countries. There are 6 that have not yet started producing energy balances. And there's 1 person who's currently developing it. So I really hope that this presentation will help you and guide you in the production of your energy balance. So now let's go back to the presentation. Yeah. So now let's see what is an energy balance. So this is an energy balance. It's the IEA format, and it's a compact source of information, as you can see. In the past, many organizations were using different methods to produce energy balances, and there was a real need to harmonize and have a common framework to establish the standard. And today this framework, it exists. It is the International Recommendations on Energy Statistics, what we call the IRES. And it enables us all to speak the same language. It's in the IRES, it defines the energy balances as an accounting framework for the compilation of data on all energy products that enters, exits, and that are consumed within the country during a specific period. Let's look more closely at this energy balance. As you can see, it is a matrix with products and flows, and it is divided into 3 main blocks. You have the supply block, where you have the production, trade, bunkers, and stock changes. Then you have the second block, which is about the transformation sector and the energy industries, own use and losses. And you have the last block, which is about the final consumption in end use sectors. in the columns, you have all the different products that are aligned next to each other. And this is the beauty of the energy balance. You see, because you're reporting all the products in a common unit, energy unit, you can really align all the products next to each other and compute that total column, which is extremely useful. Because all the products are in energy terms, you are able to calculate your total energy supply of the country. So this energy balance, it gives you the global picture of the energy situation of a country. And also because you are reporting the energy balance using a standard methodology, you're also able to compare your energy balance with other countries. Another way to present your energy balance is through the Sankey flow charts. It is exactly the reverse matrix of the energy balance table that you have seen before. So here you have the arrows that show the flows of the energy from production up from production to your left, to the right side, to the final energy consumption. You can see that here the arrows, they can be splitted, they can be combined together, and the width of the arrow, it's proportional to the flow quantity. In this Sankey chart here, you can see the example of the world energy balance. And you can see that, for example, you have on your left side the oil production, your oil imports, and then you can see how this oil is flows through the energy system up to the final consumption. So here for oil, you can see that at the world level, you have your oil production and imports that enters, and then you have some oil products also that are imported. The oil is, some of it goes to refineries to produce oil products. Then there are some exports of these oil products. Some of it goes to the power stations for producing electricity. And when you arrive to the final consumption, you can visually see that most of these oil products, it's consumed in the transport sector. So with just a quick glance, you can see for your country, which products are the most important, which sectors are consuming most of this product. And also, I recommend you to go on the IEA website and look at the Sankey page, where you can have the Sankey charts for all the countries of the world. And you can also use the timeline to see how the energy situation of a country evolves over time. So for example, if you take Australia, you can see how its energy sector has evolved from 1971 to the latest year available, which is 2018. So we have seen how the energy balance looks like, but why is it so important to create an energy balance? Having an energy balance, it has many advantages and uses. So because we are presenting the energy balance in a common energy unit, we are capable of calculating the total energy supply and consumption of the country. Also, because we are able to align all the products next to each other in a common unit, you can really see and calculate the weight of the different energy sources in your energy mix. The energy balance, it also allows you to calculate the shares of the energy consumption across the different sectors of the economic activity. With an energy balance, you can calculate indicators. If you couple the energy balance with macroeconomic indicators such as GDP and population, you can calculate the energy intensity, for example. Also, countries can calculate their dependency on energy imports or exports. And because we are using similar methods, you can compare your country's energy balance with other countries. Most importantly, the statisticians, they can use the energy balance to check the quality of the data. For example, you can use the efficiencies in the transformation sector as a check, and then discrepancies can be queried. Finally, a good energy balance, it's a good basis for making projections and forecasts, and also to check that the policies that your government is putting in place are being well implemented. So we have seen that the energy balances, it's important, it has many benefits, but how do we calculate it? The way we proceed at the IEA is that first we collect the data through the different channels. So for OECD countries, we get data from the annual questionnaires, and for non-OECD countries, we collect data from various sources, such as national publications, websites, and direct contact with countries. With all this information, we create the commodity statistics, and then from this, we apply conversion factors to derive the world energy balances. Again, let's go to the Menti website to answer this question. So the question is, what do you need to convert mass to energy units? Do you need the density? Do you need calorific values, or do you need carbon content? I'll leave you a few seconds to think about this. What do we need to convert mass to energy units? So most of you have answered the correct answer. Some people are still answering. Very good. So indeed, the correct answer is calorific value. It's the net heat content of the fuel, and it is the only information that you need to convert mass to energy units. Typically, calorific values, they are reported in units of energy per mass, that is in kilojoule per kilogram. For those who answer density, this is not true, because you use the density when you are converting a liquid in mass into volume. So it's what you need when you are converting a mass per unit of volume, for example, tons per barrel. And I saw that there was one person who replied carbon content. You need carbon content when it is the carbon content, it's the carbon dioxide equivalent that is released through the combustion of a fossil fuel. And this is what you use when you're calculating CO2 emissions. So we have seen that to create energy balances, first you need the statistics by products through the commodity balance statistics. Then you need to apply the conversion factor, which are calorific values. And then you need to do some format changes in order to arrive to your energy balance. A calorific value, it's the amount of heat obtained from one unit. It can be mass or volume of the fuel, and it is the only way to convert a fuel quantity from physical units into energy units. Also, there are some reformatting that is performed so that we avoid double counting when we are summing products together. There's also a sign convention that we apply in the transformation sector, and my colleague Nicola will go in more details when he talks about the layout. So it is very important that we collect good data for the commodity balances, but it is also important to collect good calorific values. As you can see in this table, for bituminous coal, you have your supply and your demand, they are balancing. So there's no statistical differences and everything looks okay at the first glance. But then when we want to go and calculate the energy balances, then we need calorific values. So here, this is the table of calorific values that you have. You can see that the calorific values, it varies for the different flows, which is normal. And then you apply those calorific values to the commodity balances to calculate your energy balance. But then here, you notice something weird. You can see that now you have a statistical differences in your energy balance, whereas in the commodity balances, it was 0. So here you already see that you need to query and look where something is going wrong. And if you look at the calorific values in more detail, you can see that your final consumption calorific value, which is 20 terajoule per kiloton, it's quite low compared to what you have in your supply. So production, it's 23, you're importing, the coal that you imported has a calorific value of 25 terajoule per kiloton. So how come what you're consuming in the final consumption sectors, it's lower? So you can see here that the energy balances, it allowed you to check the quality of your data. And so it's really important to collect good data, both in physical quantities and in calorific values. Now let's look into more details at the principles of an energy balance. You have to make several choices when building your energy balance. First, you have to choose a common unit of account. Then you have to choose between showing your data in net or gross calorific value. Then you have to calculate, to report your calorific values by product. Then for non-combustible fuels, you have to define your primary energy form for energy transformations that do not involve combustion. And for this, you have two methods that you can use, the physical energy content method or the partial substitution method. Also, you need to take into account the temperature adjustments made by countries. And finally, you have to know if the balance is based on a fiscal year basis or a calendar year basis. Let's look at each of these methodological choices in detail now. So first, we have to choose an energy unit. It can be any energy unit. You can use the British thermal units, you can use the ton of oil equivalents, you can use joules, you can use watt hour. At the IEA, we have opted to use for the ton of oil equivalent, which is defined as 10 to the power 7 kilocalories. And this quantity of energy, it's within a few percent equal to the net heat content of 1 ton of crude oil. I said within a few percent because the crude oil quality, it varies between countries. And so it's approximately the net heat content of 1 ton of crude oil. The choice of using the ton of oil equivalent at the IEA, it's based on the history of the creation of the IEA after the first oil crisis in the 1970s. The second choice that you have to make is whether you want to report in net or gross calorific values. The difference between the net and the gross calorific value, it's the latent heat of vaporization of the water produced during combustion. So for coal and oil, the difference between the net calorific value and the gross calorific value, it's 5%. And for natural gas and other manufactured gases, the difference is approximately 10%. In the case of electricity and heat, this notion doesn't have, there's no difference as they are not combusted. And the use of, at the IEA, we use the net calorific values, and the use of net calorific values, it's consistent with the practice of statistical officers of the European communities and the United Nations. And most importantly, it represents the useful energy. Generally, for most products, the IEA adopts country-specific, time-varying, and for some products, flow-dependent net calorific values supplied by national administrations. It's very important to remember that calorific values, they vary over time, so it changes from one year to another, and it's very important to update your calorific values every year. And in the case of coal, the IEA adopts country-specific factors that are submitted by national administrations for the main categories of coal products and also for the different flows. In the case of natural gas and crude oil, we also apply specific factors for the different flows, such as production, trade, electricity generation. In the case of oil products, the IEA applies regional calorific values, and this is in conjunction with Eurostat for the European countries. So now we know how to convert combustible fuels in energy units, but because for combustible fuels, you have immeasurable inputs in the transformation sector. For example, if we take natural gas, you know exactly how much gas is entering your electricity plant, your power plant, and you know exactly, you can measure the amount of electricity produced from the gas. So in your energy balance, it balances. But what about non-combustible sources such as nuclear, geothermal, solar, wind, wave, etc.? Here you can measure the output. You know it is either electricity or heat, but how much is the related amount of primary energy? It's very important to define this primary energy so that your balance can balance out, and this is what we will look at now. So for each of those non-combustible sources, that is nuclear, geothermal, solar, hydro, wind, tide, wave, ocean, and solar PV, there is a need to define the primary energy form to be considered. For instance, in the case of hydro energy, you have to make a choice between the kinetic energy of the falling water in the turbines and the electricity produced. In the case of nuclear energy, you have to choose between the energy content of the nuclear fuel, the heat generated in the reactors, and the electricity produced in the nuclear reactor. In the case of solar photovoltaic electricity, the choice is between the solar radiation received on your solar panels and the electricity produced. The principle adopted by the IEA is that the primary energy form is the first energy form downstream in the production process for which multiple energy uses are practical. The application of this principle, it leads to the following choice of primary energy form. So it is heat for nuclear electricity, geothermal heat and electricity, and solar thermal heat. And it is electricity for hydro, wind, tide, wave, ocean, and solar photovoltaic. we have now identified the form of the energy input, but now we need to quantify it. There are essentially two methods that you can use to calculate the primary energy equivalent of these energy sources. First, you have the partial substitution method, which now at the IEA we do not use, or you have the physical energy content method. The physical energy content method, it uses the physical energy content of the primary energy form as the primary energy equivalent. So for instance, in the case of nuclear electricity production, as heat is the primary energy form selected by the IEA, the primary energy equivalent, it's the quantity of heat generated in the reactors. So, but in the absence of country-specific information, the IEA estimates the primary energy equivalent from the electricity generated in the reactors by assuming an efficiency of 33%, which is derived as the average efficiency of nuclear power plants in Europe. For geothermal electricity, the primary energy equivalent, it's the quantity of heat. And so a similar back calculation is done where we assume an efficiency of 10%. This figure of 10%, it's only approximate, and it reflects the fact that the steam from geothermal sources, it's generally of low quality. Similarly, for solar thermal plants, the heat supply is back calculated, assuming an efficiency of 33% of the conversion of heat into electricity, which reflects the low working temperatures. In the case of hydro, wind, and solar PV, as electricity is the primary energy form selected, then the primary energy equivalent, it's the physical energy content of the electricity generated in the plant. And so here we assume that it's an efficiency of 100%. So when the primary energy form is heat, then we have losses. Let's look at a few examples. I know that this concept, it's a bit difficult to grasp at the first shot. So here, let's take a few examples to better illustrate this. Let's take the example of wind. So we have 1,000 TOE of electricity produced from wind. And for wind, we know that the implied efficiency, as I have shown you before, it's 100%. So the primary energy equivalent, which is calculated as the energy output divided by the implied efficiencies. So here it's 1,000 divided by 100%. So here your primary energy equivalent, it's 1,000 TOE of wind input. If we look at nuclear this time, so if you have 1,000 TOE of electricity output, for nuclear, you know that you use an implied efficiency of 33%. So your primary energy equivalent, it's 1,000 divided by 33%, which gives you 3,030 TOE of nuclear input. In the case of geothermal, you have two possibilities. So first, with 1,000 TOE of electricity produced, so for geothermal electricity, you apply an efficiency of 10%. So then your primary energy equivalent, it's 10,000 TOE of geothermal. In the case of heat, so with 1,000 TOE of heat produced, so for geothermal, you have an implied efficiency of 50% for heat, then your primary energy equivalent is 2,000 TOE of geothermal. Now let's use again Menti to test again if you have understood well this concept. So let's go back to Menti. So now I want to go to the next, okay. So now if you connect yourself to Menti and you use the same code as before, can you please answer this question? what is the primary energy equivalent for solar thermal with 1000 TOE of electricity produced? So here for solar thermal, so the answers are coming. So what is the implied efficiency of solar thermal electricity? Think about what I have shown you in the previous slides. So for solar thermal electricity, with 1000 TOE of electricity produced, what efficiency will you apply to calculate your primary energy equivalent? Let's see if we have a few more answers. So here the answer is 3030, and only 7 participants got the answer right. And this is because for solar thermal electricity, the implied efficiency is 33%. It's not 100% as many people have thought so. So here, the primary energy equivalent for solar thermal with 1000 TOE of electricity produced, it's 3030 TOE. Let's do another. Sorry, I went too fast. So now it's again a similar question, but this time we are looking at the heat. So what is the primary energy equivalent for solar thermal with 1000 TOE of heat produced? Before the question was on electricity produced, but here it's on heat produced. So again, please vote. So what is the implied efficiency for solar thermal heat? Some people are still answering. So most of you got the answer right this time. For solar thermal heat, the implied efficiency is 100%. And so the answer here is the primary energy equivalent for solar thermal heat with 1000 TOE of heat produced, it's 1000 TOE. So many of you understood well this concept. And now I will pass over to my colleague, Nicola Draghi, who will continue with the presentation and walk you through the IEA energy balance layout and the different uses that you can make from it. So Nicola, the floor is yours now.
Thank you very much, Zakia. Just a moment that I'm setting up my desktop, and I'll also give you the time to assimilate this concept, which are indeed very complicated, but fundamental. So screen 2, can you see my screen?
Yes.
Perfect. Okay, So let's go back to the energy balance in a tabular format, and let's see how to read it. Here we go. So you can see from the top to the bottom that we have the flows on the left side, and again, the products in the columns. For each product, this is a commodity, a balance, and the flows indeed are the consumption on the rows. Let me use the pointer to show you that, again, we can see the three blocks that Zakia already defined previously in the presentation. From production to stock change is the supply block. Then there is also total energy supply, which belongs to that block. Then we have the transformation block, which includes also energy industry on use. And finally, we have total final consumption, including several sectors. For the supply block, very important, something to notice is that secondary products will have always a zero in the production line. This is because their production actually happens in, or at least it's recorded by us, in the transformation block. Thus, we want to avoid double counting. Just to say that again, the difference between primary and secondary products that you should be already familiar is that primary products can be extracted from nature, from the biosphere, from natural reserves, while secondary products, as oil products and electricity, have to be transformed from other energy products or other conversions. Let's go then to transformation, the second block. Very important here, it's the sign convention between inputs and outputs of transformation processes. We can see for electricity plant that coal, not only coal, but also other energy fuels, but for now we only highlighted coal, is accounted with a negative sign, meaning that this is an input of the transformation process. And electricity, this is total electricity, thus not only referring to coal. Anyway, it's an output of the process, it's the output of the process, so has a positive sign. Same for crude oil, which is used in refinery and is converted in oil products. To notice here, also very important, energy balances can be used to run some checks on the data quality of your data collection. For example, here in a refinery, there shouldn't be energy gains. So the products should have less energy than the inputs. And this is the case. So we are right. We have then final consumption. And again, the fact that the balance uses a common unit across all the energy products give us the possibility to have a total column where we sum all the contribution of the single fuels. Very important in this total column is the cell about total energy supply, of course, because that is the total demand of the country. Instead, for the transformation block, in the total column, we will mostly have negative values. This because these values represents the losses that we incurred in the transformation process. Okay, perfect. Now it's time for another exercise. I will switch directly to Menti. Just a moment. Okay, too many screens. Here we go. So the question that we have now is, you can see here an energy balance, just the first 7 rows. And I would like to ask you, which country is this energy balance of? I see that you start already voting very well. I will show you again the energy balance and then we will go back to the voting. Otherwise it's difficult to guess. If I can give a hint, but I saw you were already very quick with the answers, I will look at the production row, where you can see which are the most important energy products which are domestically produced by the country. Okay, we have 16 people, 17 people voting. France and Norway are the one which have been receiving more votes. I leave again a little bit more the balance. And I think that Yeah, 27 people voted, so I think we can start discussing the answer. The correct one is France. Let's go back to the presentation and see why. You could have guessed that from nuclear production. Indeed, for nuclear, you see the value is quite big for production, and France is the second top producer in the world of nuclear power. In 2018, in the electricity mix, nuclear electricity accounted for 72% of the total mix. So really a big portion. Now, why that couldn't be Norway? If you see the value for hydro, you see that this is not very big, especially compared to the others, even though it's the second source domestically produced. Hydro for Norway, it's really a very big resource, so Norway couldn't be the case, especially if you compare to nuclear. Norway doesn't have nuclear production, so that's also exclude Norway. Saudi Arabia, not possible, because if you see crude oil production and natural gas production, that couldn't be the case of Saudi Arabia. This country indeed is importing the majority of, not the totality of its crude oil and a lot of oil products. Very well. What I want to highlight here is that from only 7 lines of this balance, you can already guess many things. For example, let me take the pointer again. From nuclear, hydro, and wind and solar columns, you can already get what is the total electricity production from these sources by converting these values in gigawatt hour. Of course, applying the correct implied efficiencies. Then you can see that this country has a very reliable electricity network and system, because can afford to trade quite a big amount of electricity, especially it's a net exporter of electricity. And finally, from international marine bunkers, you can see that the country is not landlocked, so it has access to the sea. Now, if you remember the initial slides on why we make energy balances, among the reasons, there was also the possibility to create high-level indicators. Those are very important, give us insights on the energy situation of the country, and also very useful for policymakers to make informed decisions, and also track the efficiency and effectiveness of energy-related policies. So to exploit the full potential of an energy balance, we recommend to combine that with some economic indicators, as can be population and gross domestic product. Here you can see a list of the most important ones that can be derived from energy balances, statistics, and economic indicators. Now, they can concern specific products, specific flows, or the total energy supply. Let's start with showing you some of the most meaningful ones. We start from total energy supply per capita, and you see here the development over time. Also on the right side, you have a list of other indicators that we publish in our database, and even more can be found on our website in the statistics section. So what we can say from this graph is that compared to 1990, in 2018, the total energy supply per capita, which is calculated by dividing tests over population, is higher in 2018, which means that it has grown more total energy supply compared to world population over this period. In particular, I would say from around 2000 onwards. Now, this can have several explanations. We won't go into that, but we can affirm, we can conclude from this that in general, people are getting access to more energy and more energy service. Thus, this improves their living condition and health condition. However, an increase in these indicators also means an increase in total energy demand worldwide, which possibly converts in an increase in CO2 emission from fuel combustion around the globe. Now, this is not good for the targets that we are setting to reduce global emissions. So we have to push the transition towards sustainable energies in order to provide a larger portion of total energy supply from clean and low carbon technologies. Another very important characteristics of such indicators is that they can be compared across countries, as we can see here for energy intensity. Energy intensity is very important. It's a very important measure, and often is used to assess the energy efficiency of a particular economy. It is calculated by taking the ratio of total energy supply over gross domestic product. And in general, a lower energy intensity is desired because it means that there is a more efficient allocation of the energy resources in order to generate the same amount of gross domestic product, which means wealth and good living condition. However, these indicators is very dependent on the state of development of a country. For example, developing countries will need to make some very energy intensive activities, as building telecommunication infrastructures, transport infrastructures, residential infrastructures, and so on, but also setting up certain industry to manufacture goods. This means that it's logical to expect in that stage a higher energy intensity, and also the fact that generally GDP and energy use are coupled. However, after development has taken place, historically we see a fall in energy intensity, as in the economy there are more incremental change which aim to cut the costs and improve the efficiency of processes. Also, another method to lower energy intensity is when a country transitions from an industry-based economy to a service-based economy. However, as mentioned in the beginning, you can compare your country with the regional averages. Here we have world, OECD, and non-OECD member countries, but also with countries which should be in a similar stage of development or have a similar economic structure. Self-sufficiency, very important. Another indicator, which is the ratio between national energy production and total energy supply in a given year. The rate can be calculated for each product or for the overall sum of the products, as you can see the black line in the graph. The dashed line at 100% that you see here means that the country is completely self-sufficient for that product. If we are above, it means that the country is a net exporter, so produce more than what it consumes. We saw that for United States in the coal presentation yesterday, that they are among the top producer of coal. If the country is below 100%, this means that demand is higher than production. So we need, the country needs to import some of the fuel to meet its consumption. Now, here you can see the United States. I will take again the pointer. And you can see that historically, self-sufficiency has been lower than 100% and even below 80%. But then we see that United States have very rapidly increased their self-sufficiency to go even over 100% in 2019. And for some products, they have been always self-sufficient. For others, like gas, they reached self-sufficiency recently. And for others, like oil, we saw that they were importing more than 60% of their demand at some point. But then I would say, especially from 2010, they really stepped up, increasing their production. And this is the case of oil shale in the United States, indeed. Now, you might be familiar with the Sustainable Development Goals. They were established by the United States in 2015, and they are meant to give the blueprint and measurable targets to achieve a sustainable future for everybody. In particular, goal number 7 is about energy. And it's really important in marking the political recognition that is given to energy for sustainable development. So the target of goal number 7 are set to ensure that everybody has access to affordable, reliable, sustainable, and modern energy. The IEA is the custodian agency for some of these goals you can see here on the right side. In particular, from the map, you can see the share of modern renewables, thus excluding traditional biomass, in total final consumption in 2017. Being the custodians means that we give the data, basically we collect, we verify them, and we submit the country data that are used to monitor the progresses towards the reaching of these goals. And then the share of renewables over total final consumption is the indicator for SDG 7.2. Then we have that IEA is also the custodian for energy efficiency, Sustainable Development Goal 7.3, and the indicator is the energy intensity that we saw before. So total energy supply over gross domestic product. Then we are the custodian also of SDG number 9.4, which is on emission per value, and we monitor several others, among which access to electricity and clean cooking. And you can see more on our website. On CO2 emission, energy balances are the starting point for calculating CO2 emission in million tons of CO2. From, of course, CO2 emission are only in the domain of fuel combustion. Now, I won't repeat this slide, you have already seen it. From national sources, we go to commodity statistics, we translate that into balances with the calorific values, and then we apply the 2006 IPCC guidelines to calculate CO2 emissions. This will be the topic of another presentation tomorrow, so my colleagues will give you plenty of details in this very important topic. To conclude, I hope that this presentation really helped you in understanding the fundamental dynamics of energy balances. So here are some takeaways. Good energy balances definitely require good quality statistics, both of physical data, but also of calorific values, which sometimes are even more difficult to collect. They are a very compact source of information, and very important, the comparability between products and between countries. They can also be used to perform some checks of energy statistics, as for example, checks of the efficiency in the transformation block. So you can really see if there are energy gains, if the efficiency it's not in the range where it should be, for example, for electricity conversion. And then they constitute the foundation for basic, but also not so basic, energy indicators and for CO2 emissions. Finally, about the dissemination of energy balances, we have the keyword energy statistics, which is really a summary of the most important statistics that we produce at the IEA Energy Data Center. And you can download it for free on our website. Then the IEA also publish online two important databases, the World Energy Statistics and the World Energy Balances database, as online data services. But still, you can download some free highlights on our website. You have seen already these slides many times, but really, again, to restate that they're part of our daily job to check in the manuals that all the definition are in line with international recommendation, and all the reports, the data, the tools that we have online that are produced by the Energy Data Center or that the data of the Energy Data Center contribute to. Thank you very much. That's all for